Ladies and gentlemen, imagine spending thousands on a brand new SUV, only to hear rattles, see glitches, and face breakdowns within weeks. Sounds impossible, right? But 2026 data is exposing a shocking truth the auto industry doesn't want you to see. Vehicles are getting smarter on the outside but weaker at the core. So what's really going wrong behind the scenes? And why are some cars built to last, while others start falling apart the moment you drive them off the lot? Stay with me, because what you're about to discover will completely change how you look at modern SUVs. And the idea that brand new SUVs could already be falling apart sounds like something from a past era of automotive manufacturing, an era defined by complexity, inconsistency, and slow innovation cycles. Yet even in 2026, data continues to highlight a gap between legacy production systems and what modern engineering is capable of delivering. When you examine these findings through a forward-looking lens, it becomes clear that the issue isn't just quality control, it's philosophy. And traditional SUVs are built on platforms that have evolved incrementally over decades. Layers of mechanical systems, supplier dependencies, and fragmented software architectures create a fragile ecosystem where failure points multiply. When a new model launches, it often carries over old design constraints patched with new features that were never originally intended to work together. The result is a vehicle that may look advanced on the surface but lacks structural and technological cohesion underneath. And in contrast, a clean sheet approach changes everything. Instead of retrofitting innovation into outdated frameworks, the focus shifts to first principles. Simplify, integrate, and eliminate unnecessary parts. A modern electric SUV built this way doesn't just reduce the number of components, it redefines how those components interact. Fewer moving parts mean fewer opportunities for failure. A unified software architecture ensures that systems communicate seamlessly rather than competing for control. And the reports of early breakdowns, electronic glitches, and material inconsistencies in new SUVs point to a deeper issue: overcomplication without integration. When dozens of independent suppliers contribute isolated subsystems, even minor misalignments can cascade into major problems. A sensor misread here, a software lag there, and suddenly the driving experience feels unreliable. For the driver, it's not about one failure, it's about the erosion of trust. And now consider a vertically integrated model. Hardware and software are designed together, tested together, and updated together. This approach allows for rapid iteration and continuous improvement. If an issue is identified, it doesn't require a recall cycle measured in months or years. It can be addressed over the air, often before the majority of drivers even notice it. Reliability becomes dynamic, not static. And another key factor is manufacturing precision. Legacy automakers often rely on complex assembly processes involving multiple facilities and handoffs. Each step introduces variability. A more advanced production system leverages automation, real-time data, and tight feedback loops to ensure consistency at scale. When every unit is built with the same level of precision, the concept of early failures begins to fade. And materials science also plays a role. In many traditional SUVs, interior components and structural elements are sourced based on cost optimization rather than long-term durability. Over time, this leads to wear, noise, and degradation that can appear surprisingly early in a vehicle's life. A different approach prioritizes longevity and performance, selecting materials not just for their initial appeal, but for how they behave after years of use. And software is perhaps the most overlooked dimension in these reports. Modern vehicles are essentially computers on wheels, yet many legacy systems treat software as an add-on rather than a core component. This leads to fragmented user experiences, delayed updates, and compatibility issues that can manifest as failures, even when the hardware is functioning correctly. A unified software platform designed to evolve continuously transforms the vehicle into a product that improves over time rather than deteriorating. And what the 2026 data ultimately reveals is a transition point. Consumers are no longer satisfied with vehicles that degrade quickly or require constant servicing. They expect the same reliability, responsiveness, and upgradability they experience in other areas of technology. When those expectations aren't met, the disconnect becomes immediately visible. And the path forward isn't about incremental fixes, it's about rethinking the entire system. From design and engineering to manufacturing and software, every layer must align around simplicity, integration, and continuous improvement. Only then can the idea of a brand new vehicle falling apart become obsolete, replaced by a new standard where durability and innovation are not trade-offs but fundamentals. And this shift is not theoretical, it is already happening in real time. The gap between what consumers expect and what traditional SUVs deliver is widening, and data like this simply makes that gap visible. When a vehicle begins to show signs of failure within months of delivery, it's not just a manufacturing issue. It's a signal that the underlying system wasn't designed for long-term resilience. Reliability cannot be inspected into a product at the end of the line. It must be engineered into its foundation from the very beginning. And one of the most significant differences lies in how problems are approached. In conventional models, issues are often treated as isolated defects. A faulty component is replaced, a recall is issued, and the process repeats. But this reactive model doesn't address the root cause. It doesn't ask why the system allowed that failure to occur in the first place. A more advanced approach treats every issue as a data point in a larger system, feeding back into design, production, and software updates in a continuous loop of improvement. And this is where real-time data becomes a critical advantage. When vehicles are connected, anonymized performance data can highlight patterns long before they become widespread problems. Instead of waiting for failures to accumulate, potential weaknesses can be identified and corrected proactively. This transforms reliability from a static metric into a living system, one that evolves and strengthens over time. And another factor is the speed of innovation. Legacy automakers typically operate on multi-year development cycles. By the time a new SUV reaches the market, many of its systems are already outdated. Updates are slow, costly, and often require physical intervention. In contrast, a more agile development model allows for rapid iteration. Features can be refined, optimized, and even completely reimagined through software updates, ensuring that the vehicle remains current long after it leaves the factory. And design simplicity also plays a crucial role. Complexity is often mistaken for sophistication, but in reality, it increases the likelihood of failure. Every additional component, every extra layer of integration introduces new variables that must be managed. By reducing complexity, the system becomes more robust. Fewer parts mean fewer things to break, fewer dependencies, and a clearer path to reliability. And this philosophy extends to the user experience as well. In many traditional SUVs, the interface between driver and vehicle is fragmented, with multiple systems operating independently. This can lead to confusion, inconsistency, and a sense that the vehicle is working against the driver rather than with them. A unified interface powered by a cohesive software platform creates a more intuitive and reliable experience. When everything works together seamlessly, the perception of quality increases dramatically. And energy systems further illustrate this contrast. Internal combustion engines rely on hundreds of moving parts, operating under extreme conditions. Wear and tear are inevitable, and maintenance becomes a constant requirement. Electric powertrains, by comparison, are inherently simpler and more durable. With fewer moving parts and more precise control systems, they offer a level of reliability that is difficult to achieve with traditional designs. And the manufacturing environment itself is also evolving. Advanced factories are becoming more like high-tech laboratories, where every step of the production process is monitored, analyzed, and optimized in real time. Automation reduces human error, while data-driven insights ensure that deviations are corrected immediately. This level of control is essential for achieving consistent quality at scale. And supply chain integration is another critical element. When key components are designed and produced in-house, there is greater control over quality, compatibility, and performance. External dependencies are minimized, and the entire system can be optimized as a whole. This stands in contrast to the traditional model, where a complex web of suppliers can introduce variability and delay. And ultimately, what these reports highlight is not just a problem with certain SUVs, but a broader shift in what defines a high-quality vehicle. It's no longer enough for a car to perform well on day one. It must continue to perform, adapt, and improve over time. Durability is no longer measured in years alone, but in how effectively a vehicle can evolve with changing conditions and expectations. And as this transformation continues, the industry is being pushed toward a new standard, one where reliability is not an afterthought, but a core design principle. Vehicles that fail to meet this standard will increasingly stand out, not because of isolated defects, but because they represent an outdated approach in a rapidly advancing world. And as this new standard takes hold, the definition of value in the automotive world begins to shift in a fundamental way. It is no longer anchored solely in horsepower, exterior styling, or brand legacy. Instead, it is increasingly measured by how intelligently a vehicle is designed, how seamlessly its systems interact, and how reliably it performs over time without degradation. When a brand new SUV shows early signs of failure, it exposes a disconnect between what is being promised and what is actually being delivered. And this disconnect often stems from a mindset that prioritizes short-term output over long-term performance. In traditional production environments, success is frequently defined by how quickly a model can be brought to market and how many units can be produced within a given time frame. Quality in many cases becomes something that is managed after the fact rather than built into the system from the start. This leads to a cycle where issues are continuously patched rather than permanently solved. And a different approach begins by redefining constraints. Instead of asking how to fit new technology into existing structures, the question becomes how to eliminate the need for those structures altogether. This leads to breakthroughs in architecture. Single-piece castings replacing dozens of smaller components, simplified wiring systems replacing complex harnesses, and centralized computing replacing scattered electronic control units. Each of these changes reduces points of failure, while simultaneously improving performance and efficiency. And thermal management is another area where this philosophy becomes evident. In many conventional SUVs, thermal systems are designed in isolation, leading to inefficiencies and inconsistencies. A more integrated approach treats thermal management as a unified system, optimizing energy flow across the entire vehicle. This not only improves efficiency, but also enhances durability as components operate within more stable temperature ranges. And the role of diagnostics is also evolving. In older systems, identifying a problem often requires manual inspection, specialized tools, and significant downtime. In a more advanced framework, diagnostics are continuous and automated. The vehicle is constantly monitoring its own performance, identifying anomalies, and in many cases correcting them before they escalate. This reduces the need for service visits and ensures that the vehicle remains in optimal condition with minimal intervention. And customer expectations are evolving alongside these technological advancements. Today's drivers are accustomed to devices that update overnight, improve with use, and rarely fail without warning. When a new SUV fails to meet these expectations, it creates a sense of frustration that goes beyond the specific issue. It challenges the perception of what modern engineering should deliver. And at the same time, transparency is becoming increasingly important. Data-driven insights allow consumers to see beyond marketing claims and understand how vehicles perform in real-world conditions. When reports highlight early failures, they don't just impact individual models, they influence broader perceptions of reliability and trust. This creates pressure for the entire industry to elevate its standards. And scalability is another critical dimension. It's one thing to produce a small number of high-quality vehicles. It's another to maintain that quality across hundreds of thousands of units. Achieving this requires a level of precision and consistency that can only be delivered through advanced manufacturing techniques and tightly integrated systems. When scalability is not aligned with quality, issues begin to surface quickly, often within the first year of ownership. And the financial implications are also significant. Early failures lead to warranty claims, service costs, and potential recalls, all of which impact both manufacturers and consumers. More importantly, they erode confidence. A vehicle is one of the most significant purchases most people make, and reliability is a key factor in that decision. When that reliability is compromised, it affects not just the current sale but future brand loyalty as well. And in this context, the emergence of a more integrated software-driven approach represents a fundamental shift. It aligns the vehicle more closely with the broader technology ecosystem, where continuous improvement and user-centric design are the norm. This alignment is not just about adding features, it's about rethinking the entire lifecycle of the product. And as these ideas continue to gain traction, the contrast between different approaches becomes more pronounced. Vehicles that are designed with simplicity, integration, and adaptability at their core begin to set a new benchmark. Those that rely on legacy systems and fragmented architectures increasingly struggle to keep up, not because they lack resources, but because they are constrained by outdated assumptions. And as this evolution continues, the competitive landscape begins to reorganize itself around entirely different metrics. It's no longer about who can produce the most variations of a model, or who can refresh a design every few years with minor visual updates. The focus shifts toward system intelligence, lifecycle efficiency, and the ability to deliver a product that becomes more capable the longer it exists. This redefinition exposes weaknesses in approaches that were once considered industry standards. And one of those weaknesses is the reliance on distributed responsibility. When multiple suppliers are responsible for critical subsystems, accountability becomes diluted. If something goes wrong, tracing the root cause can be slow and complex. Each supplier optimizes for its own component, but no one is optimizing for the system as a whole. This fragmented model makes it extremely difficult to achieve the level of cohesion required for long-term reliability. And in a more vertically aligned structure, responsibility is unified. Design, engineering, manufacturing, and software development operate within a single feedback loop. Decisions are made with full visibility into how they will impact the entire system. This eliminates many of the inefficiencies that arise from misaligned priorities and creates a more streamlined path from concept to execution. And another critical dimension is how vehicles handle edge cases. Real-world conditions are unpredictable. Extreme temperatures, varying road quality, and diverse driving behaviors all place stress on a system. In traditional models, these scenarios are often treated as outliers addressed only after issues arise. A more advanced approach anticipates these conditions from the beginning using data and simulation to ensure that the vehicle performs consistently across a wide range of environments. And this level of preparedness requires a shift in mindset. Instead of designing for average conditions, the system is designed for extremes. Components are tested beyond their expected limits, and software is trained to handle unexpected inputs gracefully. The goal is not just to meet minimum requirements, but to exceed them in a way that builds confidence over time. And the integration of artificial intelligence further amplifies these capabilities. By analyzing vast amounts of data, AI systems can identify patterns that would be impossible to detect manually. This enables more accurate predictions, more efficient energy management, and more responsive control systems. The vehicle becomes not just a machine but an adaptive system that learns from its environment and improves its performance continuously. And human-machine interaction also benefits from this approach. Instead of requiring the driver to adapt to the vehicle adapts to the driver. Controls become more intuitive, responses more predictable, and the overall experience more seamless. This reduces cognitive load and enhances safety as the driver can focus more on the road and less on managing the vehicle's systems. And at the same time, the importance of minimalism becomes increasingly clear. By stripping away unnecessary features and focusing on what truly matters, the system becomes easier to understand, maintain, and improve. This doesn't mean sacrificing functionality. It means delivering it in a more efficient and elegant way. Every component, every line of code serves a clear purpose. And the economic model also begins to change. Instead of relying heavily on post-sale service and maintenance, value is delivered through longevity and continuous improvement. This aligns the interests of the manufacturer and the customer, creating a more sustainable relationship. When the vehicle performs reliably over time, trust is reinforced and the need for intervention is reduced. And infrastructure integration adds another layer to this transformation. Vehicles are no longer isolated products. They are part of a broader ecosystem that includes charging networks, energy systems, and digital services. Seamless interaction with this ecosystem enhances convenience and reliability, creating a more holistic experience for the user. And as these elements come together, the contrast between different approaches becomes even more pronounced. Vehicles built on fragmented legacy systems struggle to adapt, while those designed with integration and intelligence at their core continue to improve. The difference is not just in performance but in philosophy. And as expectations continue to rise, the margin for error becomes increasingly small. Consumers are more informed, more connected, and more demanding than ever before. They expect products that work flawlessly, adapt to their needs, and deliver consistent value over time. In this environment, early failures are not mujarrad inconveniences. They are clear indicators that the underlying system is no longer sufficient for the demands of the present.